Okay, hi everyone. We are the Waku team. I'm Frank, Waku contributor. And we have Hanno and SP, who are researchers in the Waku team. Today we are going to talk about making peer-to-peer networks reliable. Can't see this word anymore. Let's do it. Do I need to point the clicker to? No. Okay, next slide. Can I say the next slide? Yes. All right, next slide, please. All right, so we have, this presentation is actually 3 presentations. We are going to start by talking about using Libp2p in end-user devices. I'll do that. Then we talk about a protocol we recently designed to make end-to-end reliability work. And then finally, we are going to talk about Waku Sync. This way? This way? Yeah, there you go, and user devices. All right, awesome. So I'll start, and then I hand the mic over to Hanno, and then SP. So first, the context of our protocols is a specific end-user app, which is called the status chat app. Allows you to have one-to-one chat messages, as well as Discord or IRC-like group community messages, and it's deployed on mobile, Android and iOS, and also on desktop, Windows, Linux, Mac. And we also have some learnings from other projects that use Waku, such as Railgun, which is a private DeFi project. And Railgun has application in the browser. And they also have mobile and desktop. Actually, the whole Railgun stack uses GS Waku, which is based on GS Libp2p. And they do have also a node in the cloud, which is Node.js TypeScript running. So that's basically various environments and applications that use Waku. As you can see, we have a lot of end-user devices. So when we started on Waku, we already learned a few years ago. We already had some lessons learned from Whisper. Don't know if, does anyone know what Whisper is? Do you remember from the original Web3 vision, we had Whisper, Swarm, and Ethereum? So we already knew at the time that we had to move away from a float sub where every node in the network resend every messages to all the nodes to using Libp2p gossip sub just to save some bandwidth. We started with DSV5, so that's the discovery, same discoveries than Ethereum, and DNS discoveries for bootstrapping. And we designed a number of protocols for end users. So for mobile phone. So on mobile phone, you can't really use gossip sub because it does consume more quite a bit of data. So we have a number of request response protocol. So you can send a message to a gossip sub node, or we call that a relay node, and they can forward it to the gossip sub network for you, as well as asking for a subset of messages to be sent to you. And of course, when you're offline, you miss messages from the gossip sub network. So when you go back online, you can use the store protocol to ask for messages you may have missed. We also have a Waku peer exchange, so that's different from gossip sub peer exchange for those who know that, which is being able to start your web app or your mobile phone and just ask for peers to a remote node. And finally, when you look at chat messages, there is not really strong validation rules, right? You can't really see a meme and say, oh, don't like this meme, and just drop the message. So in this network, you want to prevent someone to come in and inject terabyte of messages on the network, and then everyone that doesn't have a terabyte per second of bandwidth just drop from the network. So we have a rate limiting solution that use RLN from PSC, from the Privacy Scaling and Exploring group from EF, which allows you to limit the number of messages that a publisher can send on the network. And finally, we do have, originally we also have some what we call data sync or end-to-end reliability protocol, just a protocol that defines that when I send a message, I get some acknowledgement from the intended recipients. So there you go. All right, so that's the initial, we started with that, and we built that and put it in user app. So on desktop, we want to use relay, meaning that when you use status application on desktop, you do use gossip sub, so you're part of the gossip sub network. And you actually also provide some services to mobile. So when you use the app on mobile phone, the app has a Libp2p node running and will make connection to desktop node to be able to forward messages and also receive messages. And as Chad just mentioned, we do use circuit relay and NAT pass-through, AutoNAT, and various pass-through technology to be able to go through the NAT, go through the router to access the desktop nodes. On browser, we also use JS Libp2p in the browser, so we have it's a node running in the browser. We do not use any REST API web gateway, right? So the idea is to really have a decentralized network from the get-go, not using any centralized infrastructure. So we call that edge node, and they use the Light protocol. So from the browser and mobile, you're going to rely on GhostLibpSub node from the network to get and send messages. And finally, in terms of scalability, right? So if every single device is a Libp2p node and is part of the GhostLibpSub network, how do you handle a 1 million user, 10 million user GhostLibpSub network? So we split the GhostLibpSub traffic in shards, meaning that you end up with various, with a number of GhostLibpSub network, so you can reduce the traffic per device. So it looks like that. The pointer, no, I don't have. Yeah, oh, awesome. All right. So so you can see here the edge nodes, that's a mobile node, right? It's going to, when it goes back online, can do a store query to a service node in the cloud and get messages. It can also do a filter substitution to a relay node on the desktop and get that's live messages in real time. Desktop node will be connected to other nodes via relay, which is GhostLibpSub, and when it goes online, can do a store query to have messages. And here we have browser can also send messages via using a relay node that will then get propagated through the GhostLibpSub network. All right, so everything here is what we've done past few years, and now that we have applied that and make it work in the Status app, we have some more learnings. So one of the main challenge with GhostLibpSub is to know whether you're online. So you can see a bit of difference with, let's say, an IPFS node or an Ethereum node, where usually you deploy it maybe on a VPS or on a DApp node or something at home. You're going to start it and then probably going to leave it on for a while. When you are talking about desktop that may, or laptops that may change Wi-Fi connection or just close the lid and go in hibernation, the question of connectivity and am I online comes more frequently. And when we talk about a chat app, as a user, when you send a message, you can't really wait that long to know whether the message was sent. So in the case of GhostLibpSub, when you use it over TCP, you are limited by the TCP timeout, which can be set up by yourself, usually between 10 and 30 seconds, which means that if you send a message, you may have to wait 30 seconds to know that the message was actually sent, which is not great. And of course, TCP, in this case, doesn't really handle macro disconnection well. So let's say if you are disconnected for a minute or so, we will see that. If you get disconnected for 5 seconds and send a message during this period, you might not be able to know that your message didn't go anywhere. So another problem, so with a laptop, you close the lid, poof, you're gone, right? And if you had mobile devices connected to this laptop and rely on this laptop to get messages, you may have a problem. So one of the issue we had is, so we use DSV5, which is the same DHT walkthrough-based discovery protocol than Ethereum. So a laptop will advertise itself on the DSV5 layer, but then their IP may change or they may just go offline. And so what will happen is that a lot of the nodes you find on DSV5 are actually now offline. So by the time you find them, they are offline. I was just looking at this morning and we have, I think, 46%. No, wait, actually, I don't know. But then we had a lot of problems around the fact that you try to connect to a node and 30% of the node are not here anymore. So that's one of the other issues as well. And of course, on the mobile, you go offline, you go back online, you try to connect to nodes that you were previously connected to, but they may be laptops themselves and they may be offline now. Another issue is the DNS. DNS is not always reliable, especially on mobile environment where there is a lot of control from the OS, right? So both on iOS and Android, the default DNS from the system is the one set by the system. We can play around with it, but it's something to be aware of. And finally, WebSocket is, I want to say it's trash. I don't know if I'm being too harsh here, but In general, it doesn't work very well for long-term connections, and we had a lot of problem with it. And finally, so as mentioned, we do have an acknowledgement-based end-to-end reliability. So you send a message, and Alice sends a message to Bob, and Bob is going to tell Alice, yes, I received it. This, of course, doesn't work if you have 100 or 1,000 people in a chat room, because if every time you send a message, you get a 1,000 acknowledgement from all the participants, you can see how it could amplify the bandwidth. Solution for so far. So doing a lot of pings, IPFS pings, selecting a subset of your gossip sub peers and just doing pings and trying to understand, okay, did the ping fail because of me or because of you, and have some heuristics so that you can detect faster that you are the one offline. We also have pings on the protocol level. So for example, the filter protocol, where you're going to subscribe to a subset of topics and get them. You may not have that many messages, so you ask the remote node, hey, am I still subscribed to you? Are you still aware of me, or are you not forwarding me messages anymore? Which is, I would say, like a protocol level ping or application protocol level ping. Redundancy, so gossip sub with a mesh system, you have inbuilt redundancy. When you forward messages, you forward it to several other peers. So you have to rebuild, have that as well replicated for the light filter or light protocols, which means that when I send a message to laptop, I'm going to send it to a couple of them to be sure that they do forward it to the gossip sub network. And also things like our peer exchange protocol, where we ask for peers. This was initially intended for mobile and browser, but actually we decided to also have it on desktop as well as rendezvous, just so that when you start your laptop, you can have faster bootstrap and connect to a new node. And we do keep this V5 because these protocols are a bit more centralized in some way. I would say they are more prone to a Sybil attack. So you may be prone to Sybil attack when you just start, but with this V5, you do have a better decentralized peer discovery. I think, yeah, that's it. And then, so we also have so we do have this Tor protocol to check for missed messages. And so we are relying on that quite a bit. So to have this better reliability. So we will do, for example, a regular check to the Tor protocol to see if any message were missed, just asking for message ID and comparing that with messages that your app has seen, as well as when sending a message on the gossip sub layer, waiting a bit and asking a store node if they saw this message to confirm that it did go through the gossip sub layer. Of course, this kind of added interaction does impact bandwidth, and we are hoping to ramp down this extra network interaction with our end-to-end reliability protocol that Hanno will talk about. Yeah, and finally, like the check the clock was just something stupid, but like you can do as many regular check as you want, as many regular ping as you want, but when your laptop suspends, your process is stopped. So your process can just start up again, and it thinks that everything was fine when actually it was, asleep for 2 hours. So yeah. So what's next? So in terms of like reliability and how to improve it further, Hanno and will cover this end-to-end reliability, and SP will cover Waku Sync. On our side, we are looking at our different SDKs to clean the API so that developer can have a simple API that has all of this strategy available out of the box. For store, the Waku Sync is a kind of the last building block to have a decentralized store protocol and service. So next step will be to actually try it out and do a bit more engineering to make it work properly, because currently our store nodes are more or less federated. And finally, reviewing the bandwidth impact, because we basically spend a lot of energy ensuring that we have good reliability. Now that we reach this level, the idea would be then to review everything and see if we can optimize to reduce bandwidth usage. Bandwidth and connection usage in general, so any kind of network resources. All right, we do have a couple of minutes for questions before I hand the mic to Hanno. Yeah.
Regarding the implementations on mobile, which Libp2p implementations are you using? It said Libp2p native.
Yeah, absolutely. So we currently use Go Libp2p, and we're actually working towards. So we are part of. So Waku is part of the IFT, which is, and Nimbus is also part of the IFT, which means that the NIM Libp2p developer is also part of IFT. So we're actually currently using Go Libp2p, but we started to move towards NIM Libp2p. And we're starting desktop first and then mobile. Yeah, Chad. Oh, sorry, and in the browser we use GSLibp2p, and we are going to keep GSLibp2p in the browser for the, for now we just keep the JavaScript one.
Yeah, and just to add to that as well, you probably are aware of this, Frank, that we have at least a React Native demo application, and we've done some work on GSLibp2p to make it compatible with React Native. So like in our demo, we have a WebRTC, mobile to mobile React Native setup there. I don't think it's ever been tested over like 5G or 4G. So I think some of the situation might be a little bit different there. But it's just last thing I'll say on that is that actually it's quite a good use case, because it's actually helped us with quite a few of the optimizations that we did on GSLibp2p. As you know, like dialing is way more expensive on mobile battery-wise than it is in typical like laptop browser settings as well.
So yeah, so the language stack on most Waku user is a bit complex. So yes, on mobile we use Golang simply because the status code base is Golang based. That's why we use Golang on mobile. And Railgun, they use JSWaku, but they need some specific ZK library to make Railgun work. And this ZK library only works with Node.js API. So they run Node.js inside React Native on mobile for their zero knowledge library. And because they already have that, then they just use JSWaku in Node.js in React Native on mobile. So when I say we clean up the API, I mean our intent is also to go towards simplification of the code base. For example, Railgun use Electron.js for their desktop wallet, which means that they use JSWaku, which means edge node. I'm looking forward to be able to provide a full stack JS SDK that would use NIM Libp2p when you are running in Node, and use GSLibp2p when you're running in the browser, so that you can have Relay browser on the laptop, which give you a bit more privacy, but also help you to support the network more. Any other question? Awesome. All right.
I've heard by now I have to press down, right? Cool. Okay. Yes, I am Hanno. I will be presenting the scalable data sync protocol, or just it's a very early protocol, so just mention some of the high-level features. SDS, scalable data synchronization, is Waku's solution for app-level end-to-end reliability over a broadcast-type transport like gossip-sub. I think this the distinction is quite important, because you have the idea that you can create logical communication directions over a broadcast type transport, and indeed the applications creating these connections need some kind of reliability which cannot be provided by the gossip sub transport itself. We are focusing on the idea of a group communication, and we use the model of consolidating distributed logs. So if you think of a group communication where multiple participants are interested in somehow adding to a communication, but also sharing it within this group, and have a consistent view of what messages or entries are in this communication and in what order, you need some kind of reliability protocol for that. And indeed, the first application for Waku is a group chat application. And yes, we are focusing on providing some protocol that group can provide at least partial causal ordering and eventual consistency. I hope to be able to expand a little bit more on what that means if you don't know, but basically everyone in the group chat agrees on what messages have been sent and in what order they should eventually be displayed within the common view. We are focusing first on a large-scale dynamic participant groups. We believe this is the most difficult problem to solve. And if we are able to do that, in theory, you should be able to use the same protocol for the special case of, say, one-on-one communications, because that's just a group with just 2 participants. So there, as Franck has mentioned, there are some scalability challenges using existing reliability protocols over transport that are broadcast type transport, such as gossip, in our case, Waku relay. If you think of something a bit more simple, maybe you have direct interaction in a one-on-one chat or in small group chats, usually there are simple things that you can do. You can maybe have direct acknowledgement of messages between participants, and that should work reasonably well. And it should also scale well, even if your underlying transport is a broadcast type transport, because the number of interactions that are all broadcast in this network are relatively low, because they're generated by a relatively low number of participants in the communication, right? So as soon as you try and apply reliability to larger groups, you tend to have an explosion of these kind of individual interactions. Maybe acknowledgements are sent, or maybe some kind of sync requests are sent to try and retrieve missing messages or gaps within your own history. And you very quickly increase redundancy and resource usage to such an extent that the network might be flooded, right? And I think I include a very simple illustration here of how that might work. So imagine this is a group chat of 5 different participants, and they're using some kind of broadcast transport to communicate with each other. We have this red participant in the bottom trying to send a message to the rest of the group. Manages to do that. They all receive it. And now, if you're using a naive protocol, maybe this green, there used to be an animation here, and I can see there will be no animation. But imagine that this green participant tries to send an acknowledgement. It should have sent the acknowledgement just to the original recipient here, but of course it's broadcasting, so everyone receives that acknowledgement. But if this protocol is applied just as is, all of the other nodes will also send acknowledgements in the network, and this creates a massive explosion of usage, right? So this doesn't work. We need something else. Okay, so we want to design a protocol that provides partial causal ordering and eventual consistency. Again, this just means that in a reasonable time frame, everyone should be able to agree on what messages have been sent and what the order of these messages are within the group conversation. As far as possible, we want to piggyback on existing messages. So people are already communicating with each other in this group, and we just want to maybe add some extra information to their messages so that they can achieve this ordering and consistency. We're also a little bit modest, especially in the beginning, in terms of what we want to achieve. So we make it a responsibility of each participant to kind of infer whether the messages that it has published have been acknowledged by at least a sub-part of other participants in the group, maybe up to an extent we can be reasonably certain that these messages can be distributed further in the group. And we also make it the responsibility of participants to determine gaps in the causal history. If I say causal history, it means just the messages that have preceded every message that they receive, so that they can see, oh, they are. Good evening. Is this a phone call? Is it a, okay. Anyway, okay, so basically, the recipients of messages should be able to determine what messages they miss, and they can use some kind of pull mechanism to retrieve those messages. However, We are trying to limit redundancy and latency because we know that we're using gossip sub as our transport layer, right? So we prefer some kind of eager push mechanism to propagate new messages quickly in a one-to-many communication. The one is the publisher of a message and the many are the recipients. So the action of publishing to the network is just one interaction that needs to be broadcast, whereas an action of pulling messages from each of the many recipients would be many interactions. And we need to avoid that because we're trying to build something scalable over broadcast. So there is a lazy pull mechanism to try and make it as lazy as possible to get this protocol to scale. Right, okay, so what do we want the protocol to have and what did we add? Well, we added basic causal ordering using lamp or timestamps. If you don't know lamp or timestamps, it's a sequence number, a logical clock. It's very simple. Some of you might ask, why not vector clocks or something more sophisticated? Well, because those usually don't scale, or there are very complicated ways to make them scale. We have a causal dependency directed acyclic graph to detect missing messages. Simple terms, each message contains a reference to some previous messages that from the publisher's perspective just preceded this message in its own local log, which is to say, if you receive this message, please make sure that you have received it after the 2 or 3 messages that I believe have preceded this message. We include a Bloom filter to track message acknowledgements. Bloom filter, I think many here know what that is. Clever series of numbers that represent a list of IDs. In this case, a window of the history of all messages received prior to this message that's being published. That's it. So now if you want to publish a message, you can, for example, publish it via Waku Relay. This is just our version of Gossip Sub. And now on the application level, you will consider this message as unacknowledged. Because we want to prioritize eager push, we will make it the publisher's responsibility to periodically rebroadcast this message until it gets some indication that the message has been acknowledged. How can you acknowledge a message? Well, if you receive any other message from your group communication, you might be able to see that it is part of someone else's causal tag, that is to say, within the causal history of a message that you've received, this message is a dependency, we call this a dependency. Or more probabilistically, you can act the message by checking for its inclusion in the Bloom filters that are included with each message. Right, so without animation, this is maybe not going to make so much sense, but let's assume this same red participant wants to send a message, and it does so. But now instead of any acknowledgements being generated or one-on-one interactions being generated, which all must be broadcast, let's just wait for the next group message, which should come. Oh, this is it spoils the surprise. But now let's say this top left blue participant wants to publish a new message. It does so, it crafts a blue message, but it includes a reference to the red message that it just received. Broadcast that to everyone in the group. But now the original recipient, which was here in the middle, bottom middle, can actually determine that its message has been acknowledged by at least one other participant in the group, by the mere fact that there's a reference to this message in this group. But of course, everyone else in the same broadcast group or the communication group can use the same information to determine that there has been a red message and maybe they haven't received it, right? So they can detect some gaps in their own causal history. Right, so to summarize what might happen at a recipient, so they can receive a message now, they can use the lamp or timestamps, the logical clock, to place the message in its local log or in the local chat history at the right place. And we can guarantee that everyone in this communication will sort these messages or order these messages in exactly the same way. And then it can use the causal dependencies before doing this to verify that it has seen all of the IDs of messages, the references to prior messages that this message depends on, right? And if it detects that it has unmet dependencies, there are some messages that it hasn't seen yet, it will buffer this message until such time as it has received those unmet dependencies, and then process the message. Missing dependencies can be lazily fetched then as needed. This mechanism is in a sense underdefined. We use various methods within Waku. We also have a protocol called Waku Store Protocol, which is a non-broadcast protocol to retrieve such messages from semi-centralized caches, although peer-to-peer interaction can also be used to retrieve those. Yeah, just to mention that this is a very incomplete picture that I have painted. Of course, this would be a very slow mechanism and there might be some gaps. We do include in the full specification things like periodic sync mechanisms to maintain the state and reach consistency a little bit faster. We have the idea of outgoing and incoming buffer sweeps, that it just is to say each participant maintains a buffer of messages that it has published, outgoing messages, and try and verify that sufficient acknowledgement has been received, that these messages has been seen by one or more of the group. It also maintains some kind of incoming buffer where these causal dependencies, these past historical messages that you need to receive before processing this one, has indeed been received, and use some techniques to try and determine what they are from the network. Within Waku applications, we also very often have this need for ephemeral messages. These are messages that can be fire and forget, and which only have value for the applications within a few seconds after they have been published. So they don't need to be part of any reliability. If they are lost, they are lost. And no one really suffers too much from that, and we also cater for that. Yes, so I think my conclusion here is that we do think of this separation of concerns with gossip sub for broadcast, but it does not provide the kind of end-to-end reliability that most applications using Waku need. For that, we've introduced SDS. But it needs to address the major scalability concerns that we do get when using these kinds of transports for applications. And yes, it achieves some partial causal ordering and eventual consistency. And we're trying to make the scalability of the protocol tunable. That is to say, you can play around with the parameters to maybe increase the efficiency of the protocol, but make it a little bit more appropriate for smaller groups. Or if you are looking at very large groups and very large groups as reliability, you can tune down the efficiency using these mechanisms. I think that's it for the, yeah, that was it for the scalable data sync protocol. Not to be confused with Waku sync protocol, which operates on the routing layer. Should we pause here for questions before? Yeah. There is one.
Once you have this working for the chat use case, do you think it can also be used in cases where ultimately the message is resolved in more of an object than a log? Like live document collaboration is probably the one that people keep trying to build. I'm from the IPFS project. People keep trying to build with CRDTs, and it's always a little bit flaky.
Exactly. CRDTs is a problem because it generates so many interactions that's necessary. Yes, we absolutely believe. So I think if we start from this idea of consolidated log, so many use cases do actually map to this use case. Of course, there might be some devils in the detail there, but I'm quite sure
What's your time frame for that you're shooting for this
for this
chat?
protocol? Okay, so we have a specification which is out on rfc.vac.dev. Sorry, I have no a QR code here, and we have already built a quick POC to kind of show that it works, at least within the simple scenarios that we can throw at it. And we are in the moment integrating it into the status application for their group communication. And I guess then we'll have answers on how well it really works. And then, but hopefully that would be something that works quite quickly, or at least gives us the learnings to prove that it works quite quickly and make some changes. So I think within the next couple of months, we really need to see this in production. Yeah.
Hello, thank you for nice presentation. I have a couple of questions you can see, or maybe suggestions. If you go to the message format that you had shown, this one, I had one query. Since we are using that data sync as well, for example, peer's own timestamp along with the time zone, along with the last message hash is sufficient to last message hash maybe to tell what was the last seen message for me. I'm asking if
okay, so what you're referring to, I think, stop me if I'm wrong. So this forms some kind of directed acyclic graph of messages that goes back. It's like a chain of messages. And you say we are only interested in the head.
Yes.
And maybe a reference
yes,
to one.
if you are having a separate sync protocol, then maybe the complete message history is not needed.
Yes, so you're talking about the Bloom filter that might not be needed.
Not the previous, the casual history, IDC, IDB, IDA. Yes.
Yeah. Which? Yes. This is just to
That
make it a
can
little bit more faster. So we add 2 or 3 of them. Of hashes to previous messages, but you can actually just link to the previous one.
Link to the previous one.
We find that if there are gaps, you manage to find more of them more quickly. Just include fairly cheaply 2 or 3 of them.
Yes.
Yeah, but there's no. That's one of the parameters that can be tuned.
Obviously.
Yeah.
One more question. I think you have a much smaller mesh size for broadcast. You're using Gossip Sub for broadcast, and you are having still the bigger mesh size D, or it's a smaller mesh?
Our mesh is quite big, in fact. Yes, but I guess it depends on what you define as big.
Okay.
Are you referring to the degree?
The degree, yes.
Yes, our degree is currently between 4 and 8, which is a bit lower than I think the default is.
Yes.
Yeah.
Okay. If we use Gossip Sub for broadcast and we slightly modify the heartbeat to rotate between the peers, maybe on a heartbeat interval, so maybe that rotation can also help achieve the sync, because that heartbeat is getting I-haves or the IDs of the seen messages. So that rotation along with this message format can easily assure the sequence and the availability.
Yes, I
Just a
think
suggestion. Just a
you're
suggestion.
right. If I understand you correctly, I think the difference here, though, is that no matter what you do on the Gossip Sub level, which you should do, maybe to improve bandwidth and even reliability, that level, the end-to-end reliability only really relies within the application layer. And for us, these are usually within an encryption layer as well, because there can always be something that goes wrong within the multiple Gossip Sub hubs, and there's no way for the application to truly know that something has
But
gone
for
wrong.
a bigger D and everyone syncing after a certain interval along with the I-haves, it gets very difficult for someone to actually miss on message.
Yes, and that is in some sense is almost a problem, because then the applications rely only on that mechanism because it almost always works. But what we usually see is that, for example, they have very short, undetected, disconnection periods in their chat application, and it's not detected on any of the kind of TCP links, and it's impossible to know then even in the Gossip2p layer. So it's really only where the message is crafted, which is in the application, where there can be any sort of confirmation that the message has been received. But very good points, and these are things that we do look at in quite some detail.
I think we can have follow-up discussion.
Yeah,
after.
yeah, yeah.
Yes, sure. Thank you.
Go ahead.
I just wanted to mention back to the previous presentation is that Gossip2p is just one part of the picture, right? Mobile phone, browser, and sometimes desktop will rely on other routing strategy to access messages. So that plus the macro disconnection, which might not happen as often when you run like an Ethereum node, you have a laptop, you change Wi-Fi and things like that. So Gossip2p is just part of the picture. And actually, that's one, as Hanno just said, Gossip2p is quite reliable, which is a problem because it means that it works most of the time, except when it doesn't work. And if you don't have this strategy in place, then you miss messages.
What version of the PP are you using on the mobile platform? What implementation is it? It's Go.
Is Golang looking at my...
Are you having any issues with battery life on mobile devices?
yes.
All of the issues?
So, yes, that's another story. It's a long story. Okay. SP, I think, yeah. More questions or? Okay, I mean, okay, I think SP can go, and if you want more questions at the end, we can answer more questions about any of the subjects.
All right.
Let's go.
Waku Sync. So some of the nodes in the network, they store messages. And we know that Gossip2p is not perfect, and you can get disconnected for whatever reason. So you might miss messages. So the end result is some nodes have one set of the messages and other nodes another set. And Waku Sync aims to mend those sets so that they are similar again. So, oh, that's an old slide. Okay. All right. So Waku Sync is based on range-based set reconciliation. You can check the research paper, that QR code, if you want. Simply put, you need to define two things to use RBSR. So for your set, you need to define a total order and a range fingerprint function. So for any given range, you need to be able to basically have the hash of that range of elements. And now to sync between two peers, you would start with all your elements in your sets, do a fingerprint of all the full range. You would send it to the other peer. The other peer would verify that this fingerprint match or not their full sets. Of course, if it match, then you can stop. The two sets are equal. If it doesn't, then you can split this range again. For this example, you can split it in half. So again, you continue, you do the fingerprint function for the first half, you send it, then the other node verifies. If it's the same, then you don't have to continue, you can move to the second half, and then you recurse like this until you find the differences in the sets. All right. So in the context of Waku, Waku messages have timestamps and hashes. So those two combined give us the total order that we need. They also have RLN proof. We can verify if the message is valid or not. That's going to be useful, and explain why later. Yeah, and basically knowing the context Waku, we send messages. We can select range in a way that we can optimize for a use case. So messages we're interested in, and the ones that are probably missing are going to be newer messages. So that's the range selection we can do, and also the fingerprint function. We can say, for example, that it needs to be efficient because we have a lot of messages. But with the RLN proofs, we know if they're valid or not. So we can craft fingerprint function that are maybe more efficient, and they don't need to prevent kind of different attacks that in other contexts you would need to defend against. So what did we do? Yeah, that's the wrong slide. Version 1, we decided to our existing protocol, the negentropy protocol, and wrap it, and just to speed up development. So it works perfectly for our use case. Waku messages, like I said, hashes timestamp. Negentropy use the same kind of that's the same data requirement. It implements efficient tree storage, so that would be good for us. It's implemented in C++, so we built a wrapper. So Prem and I guess mostly Prem, not me. But once we had that system working, we discovered some problems. Most notably that the negentropy protocol kind of assumes that you never remove elements from your set, which we do quite a lot. We keep only a limited time window. So when that time window slide forward, we need to remove the messages that are older than X timestamp. With negentropy protocol, it's difficult to do that, and we discovered that kind of recently. QR code, you can read the protocol if you want. So with the downside being too costly for us, we decided to implement our own protocol, not wrap anything. So basically, we have now total flexibility on what we do. We can, like I said, choose the range we're going to use to sync. We control the fingerprint function as well, and basically the set of assumption that we're making when we're building this protocol is going to be very specific to Waku, contrary to when we using negentropy. Of course, the bad side is that it takes time to design and implement and test new protocols. Yes. All right. So in the Waku network, gossip sub and the RLN relay that is built on top is the way message propagate. But with Waku sync, you can also propagate messages. It's a good thing and a bad thing. The good thing is that you can now have nodes without relay that would still propagate messages slowly to the network. The bad side is that we need to verify RLN proofs that are coming through sync, because we could it opens the way for like fake messages, basically, to pollute the network. Waku Sync could be also used to maybe replace some protocols, or at least work in conjunction with other. Light pushed filter are two candidates. So basically, for light push, you would just send the message from a edge node to a full node, and then you would do a quick sync to verify that the message was actually propagated in the network. And filter, you would just do multiple sync, and then you would get the messages that you may have missed. Yeah. Any questions?
Awesome. Thank you very much for your
Yes.
time, for your attention.
Thank
Thank
you.
you.